Hello, this is a lecture on stellar evolution for my Astronomy 100 course. So let's start with the zoology of stars. So in other words, how those stars are divided into different classes. Well, as usual, as researchers, we don't like to have just a single way to measure something. We have seen that there is a connection between the color of a star and its temperature, namely blue stars are hotter and red stars are cooler. Well, what happens is that we have other ways to obtain the temperature of a star. And some of these ways include our capability to look at the spectra of stars. For example, cold stars do not show hydrogen absorption spectra, meaning that the temperature is not high enough to ionize the hydrogen around the star. And so this is a further information about the stars. This turns into a graph like this one. In this graph we see in the x-axis we see the temperature by decreasing numbers, so the temperature measured in Kelvin, and here we see the line strength, which is the darkness and the width of a line, which is more material in that precise element. Let's start as an example from the 6000, which is the measurement for our star, the Sun. Well, at 6000 Kelvin, we would see lines of hydrogen, which is this graph here, this plot here, lines of ionized iron, and lines of calcium. All these three lines would have more or less the same prominency, the same strength, meaning that there is more or less the same amount of ionized calcium, ionized iron, and hydrogen in those stars. Well, if the star is much hotter, say at 10,000 Kelvin, then the only line we would see would be just the hydrogen line. In this graph are shown temperatures around 8,000 Kelvin and 20,000, 15,000 Kelvin. And we see that for both we would have the same hydrogen line, but in this case we would see also a helium line. In this case we would see a calcium line. So this is just a further way we have to obtain the temperature just by looking at the lines in the absorption spectra. Well, this allows us to divide the stars into different classes. These different classes go with curious letters, which you can remember with "Oh, be a fine girl, kiss me." But we'll see that most of the stars are in these classes, which are called the main sequence. And here in the table you can check what is the mass in terms of solar masses and what is the radius of these stars in terms of solar radius. So the blue stars, the very blue stars, are between 20 and 100 solar masses, and their radius is around 12 to 25 solar radii. They show helium, hydrogen, ionized helium lines, and the temperature is around 40,000 Kelvin. So these are the hottest stars we can see in the sky. Well, below this table we have the red stars, which are classed as M-type, and we see that their mass can be as low as 8% of the solar mass, and the radius as well can be 10% of the solar radius, and the temperature will be like 3000 Kelvin, so they are very cool. We can see also the class where our star, the Sun, belongs, which is the G class, yellow, white, and the mass is around the solar mass, and the radius is around the solar radius, and the temperature is around 6,000. So we will see the lines of hydrogen and double ionized calcium in this example. Two guys which are named here are H. The H here is Hertzsprung, the R here is Russell. Plotted all the stars in a graph like this one. On the x-axis we have the color, on the y-axis we have the magnitude, namely the luminosity of stars, and we can see that from bottom right to up left we see red to blue stars. In other words, red stars are cool and dim, and blue stars are blue and bright. We see besides the main sequence, there are a couple of branches. There is a branch called supergiant, where we see blue and to red and bright stars. So these are completely different from these ones. And then we see another branch, which is the white dwarf branch. In other words, blue stars, but not that bright. These are the three main branches of stars we can see in the sky, but the main sequence is this one, going from bottom right to top left. Well, often you hear that the Sun is considered as an average star. Well, the Sun is considered as an average star as compared with most of the stars we have around us. But for local stars, the Sun is quite bright, as you can see. This is again the color magnitude diagram. On the x-axis you have blue to red, and on the y-axis you have the luminosity. And you can see that if you compare the Sun to the brightest stars we have around us, then the Sun is not as bright, it's quite dim. This is because the sample we are using is biased, and depending on what we are looking at, as you may imagine, farther stars are the brightest stars, and so if we want to look farther away, we have to look at brighter stars. So in this reason, in this way, the Sun will be much dimmer than the other stars. Otherwise, if we compare to the local stars, probably the Sun is one of the brightest stars, and this is what we have seen in the previous graph. What is even more interesting is that for binary stars we can obtain the mass of the stars by using the Kepler law. To obtain from the period of rotation we can obtain the masses. Well, by using these we can graph mass in the x-axis and luminosity in the y-axis compared to solar luminosity. So 1 is the Sun in this graph, and 1000 is 10,000 brighter than the Sun. Well, what happens if we put these graphs on a logarithmic scale? We find a linear behavior. A linear behavior in a logarithmic scale means a power law connecting the luminosity and the mass. And this power law, P, goes as 3.5 roughly. This means that the bigger the star, the brighter it is. So again, we connect the size of a star and its luminosity. We already know that blue stars used to be much larger, so blue stars are even the more luminous stars. Well, this is very important to understand a strange fact, that since the luminosity, which is the power emitted by stars, is proportional to the power of the mass, well, the lifetime of a star will be somehow inversely proportional to the mass of a star. To make a comparison, is just as you are driving a big truck, and this big truck is consuming much more fuel. Well, the big truck will have a less capability to drive with respect to a small car. This is because the same fuel you're using is the car itself. In other words, you are driving, and when you drive, the car disappears behind you. The bigger the car, the shorter the kilometers you can do, the shorter the way you can drive. And this is also what happens to the stars. The big stars consume, because of the high gravity, the high pressure, and the high temperature, consume more of their fuel. But since their fuel are themselves, they somehow die before the others. For example, a star having a mass 10 times the solar mass will have a luminosity more than 3,000 times brighter than the sun, and the lifetime will be 1/320 times shorter than that of the sun, meaning that if the expected lifetime for the sun is somehow 10 billion years, in this case the lifetime will be much shorter. We have a table here to show you how this happens. For example, a star like the sun is expected to have a life of 10 billion years. A star like a giant blue star can have a much shorter lifetime, predicted as just 3 million years, which in terms of the universe is a quite short time. On the other hand, a dim red star can live much longer than the universe, as we know here. This is because the energy we use is proportional to the mass through the famous E = mc², Einstein formula for the conversion mass to energy. This is quite interesting because it shows us how to use the color magnitude diagram to tell the age of a group of stars. Let's look at these two pictures. The first one on the left is a very well-known cluster, which is called the Pleiades, very close to the Taurus constellation. These are 5 blue stars, and you can guess, since they are blue, can they be very old? Probably not, because we have seen that blue stars can only live not longer than 3 million years. So in terms of universe, this is a very young cluster. Here on the right, we see a globular cluster named M55. And we can see that there are many red stars in this globular cluster. So the red color of this cluster tells us that there are many old stars. Namely, this cluster, assuming they were all born at the same time, this cluster will be much older than this one on the left. And if we give a glance at the color magnitude diagram, we see that the Pleiades are more or less all aligned in the main sequence color magnitude diagram. On the right, we see that M55 would have a completely different color magnitude diagram, showing a very prominent red giant branch here. This means that something happened in this region and acts to eliminate the stars from here and puts them in this region there. And also we can see that the stars in this part here, in this precise point, are about to die because they are the next to leave the main sequence. So this is the timeline for a group of stars as the Pleiades and M55 we have seen before. At the beginning, during the formation of stars, most of the stars belong to the main sequence diagram. We go on and we see that they align, but the very bright and very blue stars begin to disappear from the main sequence and they move slowly to the right. So these stars are dying, actually, going into the red